Hi everyone. We'll continue with the exercise numericals of first chapter. So today we will solve exercise 1.6. Then we will start with exercise 1.11. So 1.6. The question goes like this. 4-point charges QA, QB and QC and QD. QA is 2 microcoulomb. QB is minus 5 microcoulomb. QC is again 2 microcoulomb. QD is minus 5 microcoulomb. So if there is a charges like this which are located at the corners of square ABCD of side 10 centimeter. What is the force on a charge of 1 microcoulomb placed at the center of the square? So basically you have QO, I will write 1 microcoulomb. When you place it at the center of the square, what is the net force at this point? Let me mark it as A, B, C and D. So it is 2 microcoulomb minus 5 microcoulomb. The side is 10 centimeter. Square, all sides are equal. So you have QC as 2 microcoulomb, 2 and 2 minus 5 microcoulomb. So you have here O. When you have 1 microcoulomb, what is the force acting at the center? How will you calculate the diagonal? 10 AC is equal to root of 10 square plus 10 square, 10 square plus 10 square, root of 200, 2 into 100, square root of 200, 100 into 2, 10 root 2 centimeter. AC is 10 root 2 centimeter. So AO will be how much? 5 root 2 centimeter. Half of this one, half of AC. So you have 5 root 2 centimeter as AO. We need only up to here at the center. So you have QO as 1 microcoulomb. Now we will calculate the force acting at the center. So I will write it as FA first. FA at this point. So 1 by 4 pi epsilon naught. 2 into 10 to the power minus 6. So before that you have to write the equation. So it is QA QO divided by AO square. So it is 9 into 10 to the power 9 into QA is 2 micro is 10 to the power minus 6. So 2 into 10 to the power minus 6 into 1 into 10 to the power minus 6 divided by AO is 5 root 2 whole square. 18 into 10 to the power minus 6 minus 12, 9 minus 12 minus 3 divided by 5 square, 25 into 2. Okay, so this comes around 3.6 Newton. Now the direction we need to find out. This is positive, 1 micro is positive, so it will be repulsive force. That will be along OC. So FA will be along OC. Now you need to mark here. This is FA. Okay. This is FA. Similarly, you have to now find FB. What is the difference? Instead of QA, you have to write QB. So here you have 5. No need to take sign here. This sign is important when we consider the direction of the force. So you have here 5 root 2 whole square. 18, instead of 18 you will have 9 into 5 and then you have to substitute. Let me see. Okay. So for that we need this one. BO, distance BO. Okay. Note it down. Don't make mistakes. Micro 10 to the power minus 6 and the square root you have to be careful. Remember FA. FA is 3.6 Newton, that is along OC. Similarly, FB 1 by 4 pi epsilon naught QB QO divided by R square. 1 by 4 pi is 9 into 10 to the power 9. QB is 5 micro into 1 into 10 to the power minus 6 divided by 5 root 2 whole square. 45 into 10 to the power minus 3 divided by 25 into 2. So this comes around 9 Newton. This is minus positive, so it is attractive in nature. It is along OB. So here you have FB vector. Okay. Please keep in mind, this is the direction. This is minus sign, so that is why we will write here as FB as 9 Newton along OB. Important numerical. Next we will go with FC. So this is simple. It is 2. The value has to be same. So FC should be equal to 3.6 Newton. Now what should be the direction? It should be like this, FC. Here this one and this one, so it is repulsive, both are positive. So it has to be along OA. Similarly FD has to be 9 Newton because magnitude is the same. Sign is also same, but it is attractive in nature. This is FD. So 9 Newton along OD. Okay. So now you can see here FA, FB, FC and FD. So 3.6 and 3.6. These two are same. These two are same. Magnitude is same, but all are in the opposite directions at the center. So the net force will be 0. Net force at the center of the square is 0 Newton. It is 0 Newton. I hope this is clear. So be careful with the sign and also when you do the calculations. So from there you can take the directions. So from the directions you can conclude what is the net force. So if it is in the same direction you need to add. If it is like this in opposite directions at all the 4 sides, then it will cancel each other and the resultant force is 0 Newton. Fine. Next we will proceed with exercise 1.11. Up to 1.10 I have completed in the previous section. So today we will start with 1.11. The next concept. Next exercise. A polythene piece rubbed with wool is found to have a negative charge of 3 into 10 to the power minus 7 coulomb. Minus 7 coulomb. So estimate the number of electrons transferred. So first one, you need to calculate the number of electrons transferred. So what is the step? What is the equation? We have Q is equal to N into E. N will be equal to Q by E. Q is given 3 into 10 to the power minus 7 divided by E is charge of each electron 1.6 into 10 to the power minus 19. So from this you will get the number of electrons, total number of electrons. This comes around 2 into 10 to the power 12. You just calculated 3 by 1.6, you get 2 into 10 to the power 12. Next, part B in this one. Is there a transfer? Sorry, the first part you have from which to which? From where the electrons are transferred. So electrons are transferred from polythene to wool. Why? Because it is found to have negative charges. Polythene is found to have negative charges. So electrons are transferred from polythene to wool. So second part is there a transfer of mass from wool to polythene? Is there a transfer of mass from wool to polythene? Yes, there is a transfer of mass because each electron has a perfect mass. So there is a transfer of mass from wool to polythene. So how much is that? Mass of each electron into total number of electrons. That is how you calculate the total mass transferred from polythene to wool or wool to polythene. So each electron has a mass of 9.1 into 10 to the power minus 31 kg. So total mass transferred will be equal to mass of each electron into total number of electrons. So it is 9.1 into 10 to the power minus 31 into 2 into 10 to the power 12. 18.2 into 10 to the power minus 31 and 12. 9 minus 19. So this is the total mass transferred. So 1.8 into 10 to the power minus 19 kg. Even though the mass is very less, it is of the order of 10 to the power minus 19, but still there is a transfer of mass. Okay. So this is regarding exercise 1.1. Next is 1.12. Again you have two parts. Two insulated charged copper spheres A and B have their centers separated by a distance of 50 centimeter. So you have two spheres A and B which are separated by a distance of 50 centimeter, 0.5 meter. What is the mutual force of electrostatic repulsion if the charge on each is 6.5 into 10 to the power minus 7. So each has a charge of 6.5 into 10 to the power minus 7. QA is equal to QB. The radii of A and B are negligible compared to the distance of separation. So that means you need not consider the radius of each, otherwise you have to consider. But in this one we don't have to consider. So you just have to find out the distance, just have to consider the distance of separation and then find out the electrostatic force of repulsion. Okay. So just substitute. So F is equal to 1 by 4 pi epsilon naught QA QB by R square. Same. 9 into 10 to the power 9 into 6.5 into 10 to the power minus 7. Again it is the same. 6.5 into 10 to the power minus 7 divided by 5 into 10 to the power minus 1 whole square. Always substitute in meters. 0.5 meter is nothing but 5 into 10 to the power minus 1 meter. Substitute the values. So the answer comes around 1.5 into 10 to the power minus 2 Newton. The simple one, part A. Just substitute QA, QB and R values. Now second part, in that part B, what is the force of repulsion if each sphere is charged double? So you have QA is equal to QB is equal to 2Q doubled, and the distance between them is half. So nu R is R by 2. Nu R will be R by 2. So what is the force? So again the same thing, 1 by 4 pi epsilon naught 2Q into 2Q divided by R by 2 whole square. So 1 by 4 pi epsilon naught, we will simplify it and then we will substitute. 4Q square divided by R square by 4. Okay. This will go to the numerator, 4 into 4 16. So nu F or F dash is equal to 1 by 4 pi epsilon naught 16 Q square divided by R square. This 16 is one extra for the previous one. So F dash is equal to 1 by 16 into 1 by 4 pi epsilon naught Q square by R square. This is the one which we found out in the first case. 16 into 1 point, I think it is around 1.5. So 1.5 into 10 to the power minus 2 Newton. So new force is found to be 0.24 Newton. So it is found to be 0.24 Newton. Okay. Again the simple one, just substitute the required options and simplify it so that you can substitute the value of the previous solved question. Okay. So this is the new force. Next, 1.13. Suppose the spheres A and B in exercise 1.12 have identical sizes. A third sphere of the same size but uncharged is brought in contact with the first, then brought in contact with the second, and finally removed from both. So what is the new force of repulsion between A and B? So using exercise 1.12, the value, so that means we have the value of charge Q as 6.5 into 10 to the power minus 7 and distance as 50 centimeter. Correct? So now what is that question? You have two spheres of same radii separated by a distance of 50 centimeter. Now there is a new uncharged one. Say that I will write it as Q plus C uncharged is brought. Now we have already seen when two spheres are brought closer, charges from the charged body is transferred to the uncharged body so that it becomes equal. So now how much I will have? Both I will have it as Q by 2 and C as Q by 2. Okay. Now what is the step? So now from here C is removed and then brought in contact with B. B already has Q. Now C has how much? Q by 2. So what I will have? Q plus Q by 2. You have to average that. 3Q divided by 4. So that means B and C both have 3q by 4 coulomb of charge. Now calculate the force of repulsion between A and B. So you know that QA has q by 2 and QB has 3q by 4 charge. Using these two values, you need to find out the force of repulsion. So F is equal to 1 by 4 pi epsilon naught QA QB divided by R square. So it is 9 into 10 to the power 9 into QA is q by 2 into 3q by 4 divided by 0.5 into 10 to the power 5 in 0.5 whole square. 50 centimeter, 0.5 meter. So substitute these values. So 927 into 10 to the power 9 into q square divided by 4, this 4 into 2, 8 into 0.5 square. So substitute the value of q and then the answer will be around 5.7 into 10 to the power minus 3 Newton. 5.7 into 10 to the power minus 3 Newton. Next is 1.14. Exercise 1.14. So the figure is given. You have positive charges, negative charges, deflection 1, 2 and 3. It shows the tracks of 3 charged particles in a uniform electrostatic field. Okay. So give the signs of 3 charges. You have to tell which is positive charge, which is negative charge, and this is x direction, this is y direction. Which particle has the highest charge to mass ratio? This is what you have to calculate. Okay. So now these two 1 and 2 will have negative charges. Why? Because you can see that the deflection is along the positive side. So 1 and 2 will be negative in nature. And the third one should be positive charge, because it is attracted towards the negative one. And moreover, this third one will have higher deflection. Deflection will be more, because we have this S is equal to ut plus half at square, right? So we will take this as the horizontal one, we will not consider. So I will take it as h. Height we will see, height or deflection 0 plus half. Instead of a, we know that f is equal to m into a is equal to f by m. M in the sense we can take it as E charge, okay, or mass of the positive charge or the negative charge. So f by m into t square, correct? So now this we will take it as constant. So h is directly proportional to f by m, correct? So h in the sense deflection. If deflection is more, then this ratio is also more. What ratio they have asked? They have asked charge to mass ratio. So now you can write this one, charge to mass ratio. So this F electric field you can write, correct? So F is directly proportional to the charge. So charge to mass ratio, Q by M. So if height is more or deflection is more, then its charge to mass ratio is also more. So this is regarding exercise 1.14. So these two are negative charges, the third one is positive charge, and if deflection is more, then its charge to mass ratio is also found to be higher because it is directly proportional. Okay. Next is 1.15. Consider a uniform electric field. So E is given 3 into 10 to the power 3 I cap along x-axis Newton per Coulomb. So these are simple one. What is the flux of this field through the square of side 10 centimeter? So square of side 10 centimeter, 0.1 meter, whose plane is parallel to the YZ plane. So that is the first part. Next is, what is the flux through the same square if the normal makes some angle? So now you have to calculate this flux phi. Before that, so if you have this phi, E dot delta S, correct? Delta S is the surface area. So now first calculate delta S. Delta S will be 0.1 into 0.1, 10 to the power minus 2 meter square into I cap. Okay, considering the I cap only, electric field. So this is 10 to the power minus 2. Now calculate the flux. E is given 3 into 10 to the power 3 I cap dot 10 to the power minus 2 I cap. I cap dot I cap is 1. So it is 30. What will be the SI unit? Electric field is Newton per Coulomb. Delta S is meter square. 30 Newton per Coulomb meter square. This is a simple numerical. So now you have to find out part B. Now theta is given to be 60 degree. So if the angle is 60 degree, you have to calculate the flux. E dot delta S, E delta S cos 60. Cos 60 is half, E dot ds is this much. So you have 30 into half, it is 15 Newton per Coulomb meter square. Newton meter square per Coulomb. So this is regarding exercise 1.15. The simple one, but be careful with centimeter to meter conversion. Even though it is simple, there are chances of making mistakes. So be careful and then solve. So if this is right, you will get the second part also the correct answer. What is the net flux of the uniform electric field of exercise 1.15 through a cube of side 20 centimeter? Oriented so that its faces are parallel to the coordinates. So if I have this, we have considered along x-axis because I cap was given. So if you have a cube, you have to find out the flux. So the flux entering in the YZ plane is same as the flux moving out of the YZ plane. Correct? We will consider it as YZ plane because now it is I cap. So we have to consider, now this is X axis, Y and Z. So this plane, if you consider, number of field lines entering per unit area is same as number of field lines coming out of it. So the net electric flux through a cube is 0. Okay, so that is 0. This is what the answer for the 1.16. Next is 1.17. Careful measurement of the electric field at the surface of a black box indicates that net outward flux through the surface of the box is 8 into 10 to the power 3. meter square per coulomb. Again you have two parts. What is the net charge inside the box? Net charge, Gauss law. Second part is, if the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or why not? Again the simple one. So first is Gauss law. You have to calculate phi. Phi is equal to Q by epsilon naught. Now how will you find out this epsilon naught value? You need to calculate Q. So phi into epsilon naught. See the simple one. We know that 1 by 4 pi epsilon naught is nothing but 9 into 10 to the power 9. So epsilon naught will be equal to 1 by 4 pi into 9 into 10 to the power 9. You can substitute this value instead of remembering this epsilon naught value, which is 8.854 into 10 to the power minus 12. So you can substitute this value here. So Q will be equal to 8 into 10 to the power 3 into 1 by 4 pi into 9 into 10 to the power 9. Okay. You can simplify it. 2 and 9, 10 to the powers, you can simplify, and then the answer comes around 0.07 into 10 to the power minus 6 coulomb. Minus 6 is nothing but micro. So you can write it as 0.07 micro coulomb. So this is for the first part. Okay. So second part they have asked, so if the flux is, whether the net charge inside the box is 0 or not, can you conclude that there are no charges? Okay, so that was the question. No, you cannot tell, because we can only tell that the net charge is 0. So there might be equal number of positive charge as well as negative charge, but we cannot come to the conclusion that there are no charges at all. You cannot conclude that. You can only tell that net charges are 0. Please don't come to the conclusion that there are no charges at all. Okay, so this is the answer for 1.17 B part.